Good morning and good evening, good afternoon, based on where you are joining in this VLSI Design 2022 and the conference on embedded systems design. Today, we are on the third day of the paper presentation and the fifth day of the conference. And in the first half today, this is in track 2, auditorium 2. We are on a technical topic paper session in 5B track on test and reliability and power electronics domains. As we know that test and reliability plays very important role in terms of any embedded system and a VLSI-based systems operation, including its a platform level, system level, and SoC level testability, as well as the long-term reliability aspects, and power electronics that defines the way we interconnect our power systems and ensure that the mobile devices as well as the other connected devices, they get powered up for the maximum amount of time in the low power environment. So in this session, we have a very interesting 5 set of paper presentations, starting from the first one, that 5B1, which is titled as Criticality-Based Reliability from Rowhammer Attacks in Multi-User Multi-FPGA Platform. The paper will be presented by Krishnendra Guha and along with his co-author Amlan Chakraborty, and they're from University of Florida. So, and then we have on the remaining 4 papers. We'll start with the first paper now. Please go ahead, Krishnendu.
Hello everybody. In this session, I will be presenting to you our research article which is entitled Criticality-Based Reliability from Rowhammer Attacks in Multi-User Multi-FPGA Platform. Myself Krishnendra Guha, I am a postdoctoral research associate in University of Florida, and this is also co-authored by Professor Amlan Chakraborty from University of Calcutta. So, the contents of this presentation are as follows. First, we will be starting with an introduction, followed by a brief background. Then I will be discussing the system model and the related threat model. Then I will be discussing the proposed security mechanism, which is first analyzed based on the redundancy-based approach, and we analyze its limitations, and then we present our self-aware approach. Finally, we present our experimentation methodology and our results, and finally conclude. So, let's start with an introduction. Presently, we are in Industry 4.0, where flexibility and reconfigurability of the processing resources is of utmost importance. And for this, the system designers heavily deploy reconfigurable hardware or field programmable gate arrays, that is the FPGAs, into our embedded systems, right? So, these FPGA-based embedded systems may be accessed by multiple users simultaneously. Some of the users may be executing high critical tasks, and some of the users may be executing low critical tasks. But what is the problem over here? The problem is that many of the users may not be genuine. Some of the users may be adversaries and try to jeopardize the task executions of genuine users. So, our major contributions in this article are firstly to analyze Rowhammer attacks on real-time mixed-critical tasks for a multi-user, multi-FPGA platform. Then we explore how redundancy-based approach can mitigate this issue and also analyze its limitations. Then we propose a self-aware approach that provides criticality-based reliability and facilitates decentralized control. Okay, so let's discuss a brief background. So, attacks in a multi-FPGA platform may be broadly classified into 4 types. The first one is attacks from malicious service providers. The second one, attacks from malicious bit streams or reconfigurable IP providers. The third one is malicious FPGA tools, and the fourth one is the malicious co-users or malicious co-tenants, which is our present focus, right? So the malicious co-users may cause 2 types of attacks. The first one is the passive attacks, that is caused by leaking secret information of others via side channels, and the second one is the active attacks, which in the present case they do by changing the memory contents of other users via Rowhammer attacks. So the first one, that is the passive attacks, that is the leaking of secret information via side channels, have been discussed previously, and also its countermeasures have also been provided. But the second type of attack, that is the active attacks due to Rowhammer, was discussed previously, but its mitigation techniques were not presented. Moreover, for mitigating such type of Rohammer attacks for real-time mixed critical tasks is also not focused in previous work. Okay, now let's discuss the system model. So basically we consider a multi-FPGA platform. So what happens over here is that they are comprises a CPU plane and an FPGA plane. The CPUs and FPGAs are connected via PCIe interfaces. The CPUs can communicate among themselves via a shared CPU communication bus, and the FPGAs can communicate among themselves via shared memories, right? And each FPGA can be accessed by multiple users. So the FPGA fabric is basically partitioned into several portions which we call virtual portions, and each portion is dedicated to a particular user for executing its task. And associatedly, there is a local DRAM in each FPGA, and this local DRAM is also partitioned, which is accessed by the respective users. So uh, for about the tasks, there are two types of tasks, real-time tasks. One is the periodic and the other one is the non-periodic. So for periodic tasks, we know is arrival time, deadline, reconfiguration time and execution time. However, for non-periodic tasks, we do not know when the task will arrive and when it will be its deadline. So non-periodic tasks have to be handled at runtime. But for the present case, we only consider periodic tasks. So what is the threat model over here? The threat model is that a user may be malicious, right? So uh, let us consider three users over here, and we also consider that the FPGA fabric is partitioned into three parts, and each part is accessed by a particular user. So now let us consider that the task execution of U1 is high critical. However, the task execution of U2 and U3 is low critical. The problem over here is that U2 is an adversary, and basically it accesses its memory in such a manner that it may cause the bit flips in its neighboring memory. For example, if U2 is a malicious user and accesses row 4 in such a manner that it causes bit flips in row 3, which is basically accessed by a genuine user U1, then what will happen is that the results for U1 will be associated with error, and as U1 is executing a real high critical task, right? So the it may cause fatal consequences also. So what is the security mechanisms for this? The first one which we can propose is a redundancy based approach. So what happens in a redundancy based approach is that we replicate the task instances and we basically schedule the tasks in different FPGA platforms, right? For the present case, what we have done is that we have considered three redundant task executions per task, and then a majority pooling is performed by a centralized controller, right? So the centralized controller basically acts as an interface between the users and the FPGA platforms, and the centralized controller schedules the tasks in different FPGAs at different time instances, and on getting the results back performs a majority pooling and passes the results to the respective users, right? So this type of redundancy based approach is pretty much accurate, but what are the limitations? The limitations are that as three task instances needs to be executed, hence triple is the area and power overhead, thus the cost increases at least 3 times. Okay, the second limitation is that the strategy is quite named and it is quite simple also, and it basically induces unnecessary redundant executions in normal scenario also. That is, if there is no thread also, yet uh, each task have to be executed 3 times, right? So this is not beneficial to the service providers and users. Why? Because the service providers can cater to more users in those redundant task spaces, right? And the users, it is not beneficial. Why? Because the users have to pay high price, right? So if the third limitation is that if the centralized controller gets affected, then the entire system will halt. Therefore, our objective should be to follow a decentralized approach, right? Okay, so for the self-aware approach, what we have done is that we have created several low overhead self-aware agents, and we basically associate it with each FPGA platform, right? And these self-aware agents have access to the FPGAs as well as to a global DRAM memory. And these self-aware agents can communicate among themselves via shared memories. So our proposed methodology is a hybrid offline-online mode mechanism, right? So, and these self-aware agents, there is no centralized control for these self-aware agents, and these self-aware agents work basically in a decentralized mode of control and ensure security. So, what we do in the offline phase is that we do a lot of testing, okay, to find the number of memory accesses per unit time, which we entitle as maput, that may cause bit flips in adjacent memory locations, and this is stored in the self-aware agents. And post deployment, that is in the online phase, the self-aware agents basically monitors the maput of user programs, and on detecting deviation from recorded values, it understands that a vulnerability may be associated. And to ensure security, it communicates with other agents via shared memories and transfers the task for execution in another FPGA platform. But over here, not all tasks are transferred. Only the high critical tasks are transferred and not the low critical tasks. And if there is some associated space, then only the low critical tasks are transferred. So the priority comes for high critical tasks, and if this high critical task completes and if there is time and there is space, then only the low critical tasks are sent, right? So this is essentially a criticality based reliability approach. So now the malicious users are basically warned until the normalities are restored. Several policies are followed, so like for ensuring security. So what are the policies? Like generating buffer memory rows or supplying the local memory locations of its users, or prior exchange of tasks with other self-aware agents are done to ensure security till the normality is restored, right? Okay, so this is a demonstration of the self-aware approach where the three redundant tasks are scheduled like the redundancy based approach, but the last two redundant executions are not performed until and unless there is an anomaly. So these spaces provides the buffer spaces for the non-periodic tasks, which if arrives will be executed in those spaces, right? And these self-aware agents basically communicates with each other, and if there is some anomaly, then it transfers firstly is high critical task, and if there is space, then the low critical task, right? Okay, now let's discuss the experimentation and results. For experimentation, we have performed with Intel Aria 10 FPGAs, and the crypto tasks like AES, DES, and RSA are considered the high critical tasks, and for the low critical tasks, we have considered the HLS 1992 benchmark. And for malicious tenant operations, the tasks related to random memory access that causes hammering in the neighboring memory space are used, which are essentially loop-based programs, right? And for and we have basically carried out several simulation-based experiments to determine the success rate of high critical and low critical tasks, right? And for results, firstly we present the error analysis, which is basically a graphical representation of the number of flips encountered due to the number of hammering made by a malicious tenant program at various operational frequencies. And as evident from the presentation, the number of flips increases with the increase in hammer rates and operational frequency. And moreover, as the number of cells in a memory row is finite, hence the number of flips is steep in the beginning and then stabilizes. Okay, now we discuss security overhead. So the security overhead is analyzed with the increase in the number of FPGAs and the increase in the number of tenants. So what we find is that the overhead due to a self-aware agent over the FPGA platforms is constant. However, with the increase in FPGAs, the number of shared memories also increases, and hence the overhead increases exponentially. However, increase of overhead with increase in number of tenants is linear, due to the fact that the amount of additional logic required for monitoring each tenant program is directly proportional to the number of tenant programs, right? Next, we discuss the task success rate for high critical tasks. So this is analyzed with the normalized relative task deadline and the number of tenants. So what we find is that the task success rate increases with the increase in the relative task deadlines. Why? This is because uh, with increased relative deadlines, more is the time available for finishing the tasks in other platforms, right? And the task success rate essentially decreases with the number of users, as probability of number of malicious users will be more and less will be the slack time for executing the affected task. And now we discuss the task success rate for low critical tasks. As low critical tasks are preempted for execution of high critical tasks, hence the task success rate for high critical tasks is more than the low critical tasks. However, the trend of variation of task success rate is same for this high critical and low critical tasks. So, to conclude, what we can say that is that multi-tenant access to an FPGA and associated memory is allowed by service providers. However, this may cause security issues, and one of such issues is the row hammer attack. So, in this work, we explored initially how redundancy-based approach can facilitate security and associated limitations. Then we propose a self-aware approach where decentralized control and security is facilitated via self-aware agents as per the task criticality, and these self-aware agents monitor the memory access per unit time for tenant programs, which we entitle as Maput, and on detecting Maput values exceeding a certain threshold, it communicates with other agents and outsources tasks for safe execution in other FPGA platforms. And as evident from our graphical results, the overhead of self-aware agents is quite nominal, and the high task success rate for both high critical and low critical tasks during a task depict the prospects of our proposed mechanism. So, finally, a big thank you.
Okay, thank you, Krishnendu, for your nice paper and presentation. Any question from audience? Yeah, if there are no questions from audience, I would like to ask one to Krishnendu and team. Can you please explain that in which FPGA platform it has been really implemented, and how is the result looking for some of your experimentations?
Okay, so basically we have implemented it on this Intel Arria 10 platform, and for the results, basically we have taken a set of benchmark tasks of hardware benchmarks, and we have created a series of periodic and non-periodic tasks so that we can analyze the task success rate for the periodic task and the task rejection rate for the non-periodic task. And from our results, we are the mechanism is working fine, and so the graphical results proves that, right?
Good. Thank you, Krishnendu and team. So if there are no questions, we'll go to the next presentation, that is on 5B2, which is the topic is the pulse width modulation technique for generation of multiple analog voltages for on-chip calibration. It will be presented by Rajat Vasudevamurthy from BMS College of Engineering. Please go ahead, Rajat, with the presentation.
Very good morning and welcome to this presentation. My name is Dr. Rajat. I'm serving as an assistant professor in the Department of Electronics and Communication Engineering at BMS College of Engineering, Bangalore. And the title of my paper is Pulse Width Modulation Technique for Generation of Multiple Analog Voltages for On-Chip Calibration. And my presentation is organized as follows. I start out with the motivation for this problem and briefly talk about the state of the art, and then talk about the solution which is proposed in this paper, then present simulation results, and finally conclude. So typically the VLSI technology has been primarily driven due to the digital designs. right? And then that is driving the technology towards the deep submicron nodes. And it was noted more than 15 years ago itself that in these deep submicron processes, the time domain resolution of a digital signal edge transition is superior to voltage resolution of analog signals. So thereby, buoyed by this particular observation, there have been a lot of research effort which has been directed towards designing analog circuits which are either digitally assisted or digitally calibrated. And one of the most important circuits which has come is the ADCs, right, where ADCs are designed based on the time measurement concepts, either using a time to digital converter based approach or a VCO based approach. So in time to digital converter, you have basically a time delay, which is characterized by this time to digital converter, which will convert this delay, which is essentially analog in nature, to a digital code word. And in the VCO, as is very obvious, the voltage is going to control the output frequency of the VCO oscillator. And based on that, the conversion of the test voltage into a digital code is done. Okay, so typically the delay of the delay element which is employed in these ADCs will typically vary with the PVT variations, process voltage and temperature, and thereby typically a calibration step will be required. All right, so here let us look at this particular problem where we have essentially a voltage to time converter, and which is going to convert the test voltage or the calibration voltage into a delay. This delay could be taken on a particular clock, which I'm calling as the sampling clock on this particular slide. So essentially, the sampling clock will be delayed by an amount which is determined by the test voltage or the calibration voltage. And this job is done by the voltage to time converter. And this delay is converted into a digital code by the time to digital converter. But for the process or the purpose of this particular paper, we will concern our efforts only with the voltage to time converter. And I will measure the delay which is given by this voltage to time converter directly without bothering about the TDCs. There are multiple architectures which people have proposed for TDCs. There are various architectures, but for this particular purpose, we will not consider that. All right, so basically the idea here is to generate voltages which can calibrate the VTC. That is the basic problem. And how do you generate voltages on chip? So the most important technique is the band gap reference, right? So in the olden days, when people did not know about the PTAT current source, people only knew that the voltage of a diode is going to reduce with temperature. Once the PTAT was discovered or invented, then we have this concept of band gap reference. But again, that is going to be a pretty complex circuitry, right? So maybe it's too much of an overkill for calibration voltage generation. So based on that idea, though, the Lu and others have proposed a sub-threshold CMOS voltage reference without having the BJTs or resistors. Again, the drawback of this particular circuit is that it can generate only one particular voltage once you have fabricated on silicon. And going forward, HK Krishnamurthy and others have proposed a technique where they have developed a fully integrated voltage regulator on chip, right, which is suitable for generating multiple supply voltages for DVFS, that is dynamic voltage and frequency scaling. But as you can see, the components which they use are pretty large, right? They have on-die magnetic inductors, cascode power switches, ADC, DAC comparators, and so on, which could be, again, too much circuitry for generating calibration voltages. And Malloc and others have come up with a very interesting technique where they take a few digital square waves. In that paper, they have proposed that they will take 5 digital square waves, all of 50% duty cycle, but with slightly differing phases, where they will combine all these digital square waves to get a sinusoidal signal. Okay, and they've reported a SNDR of 52 dB at 166 megahertz, which is quite attractive. Only thing is they need a 12-bit shift register, 5 double-ended buffers, 10 non-overlapping buffers, and 5 fully differential current steering branches, with the current ratios being such that the harmonics, especially the odd harmonics of the 50% duty cycle square wave, the 3rd, 5th, 7th harmonics have to be cancelled. The higher order harmonics, of course, can be cancelled by a lenient low-pass filter. But in order to cancel the lower order, that is the 3rd, 5th, 7th, etc. harmonics, the current steering branches, the ratios have to be very, very accurately manipulated. So in order to do this, again, they are using 5 bias voltages, right, through a calibration step so that they will get these ratios in an accurate manner. Okay, so although the technique is very interesting, still they need the bias voltages which are required for a calibration step. Okay, so with that background, now we will come to the proposed solution, right? So basically here we are having a voltage to time converter, and our job is to generate a voltage which can be used for calibrating this particular voltage to time converter. Okay, so the proposed approach is to have an inverter. Okay, and then to have the input of the inverter as a clock, which I will call as the control clock, right? And notice that when this control clock is low, the PMOS will be turned on and the capacitor will charge towards Vmax. Okay, and when this control clock becomes high, then the NMOS will turn on and the capacitor will be discharged towards ground. Okay, so based on the duty cycle of this control clock, right, that is going to determine the voltage which will be sampled, or which will be the voltage to which this capacitor is going to be charged. Okay, although people typically talk about the duty cycle as a percentage of the time for which the clock is high as a fraction of the time period. Here, I will just take the duty cycle as the percentage of the time for which the capacitor is charged. Okay, so thereby the duty cycle of the control clock is going to determine the capacitor voltage, and the voltage which is now on the capacitor, that is going to determine the voltage, the delay of the given by the VTC. So I will have another clock, let me call it as a sampling clock, right? This sampling clock is essentially going to sample the voltage which is there on the capacitor, in the means that this sampling clock will get delayed, and that delay is going to depend upon this particular voltage. Okay, and you can see here, it's easy to notice that with varying duty cycle of this clock, this voltage is going to vary, and with this varying voltage, you have different delays which will be given by the VTC. Okay, so now the question will come, so what should be the time period of the sampling clock, right? So essentially, you can see here that during one clock period of this control clock, the capacitor voltage is not constant, it's going to be changing, right? So when the clock is low, the capacitor is charging, and when the clock is high, the capacitor is going to discharge. So this capacitor voltage is constantly changing through the period of the control clock. Okay. So essentially what I need to do is I need to find out what is the average value of the voltage which is there on the capacitor. Okay. So what I do is the clock period, I will keep it slightly greater than the control clock period. Right? Why do I do that? That is because since I want to find the average value of the capacitor voltage, I need to be able to sample different voltages on the capacitor, right? So if my time period of the control clock and the sampling clock were same, then in every clock period, I will see the same voltage on this particular capacitor, right? That won't help me in averaging. Okay, so this TS, I will keep it slightly more than TC, so that in every clock period, I'm going to sample a different voltage on the capacitor, right? And then when I measure the delay in each period and then average it, hopefully I will approach the average value of the voltage of the capacitor. Okay, so this is the basic idea. And as an example, in the simulation results, what I've done is I've used the control clock period to be 4.5 nanosecond, the sampling clock period to be 5 nanosecond. And essentially, the period of the output clock, right, or the delays which I'm going to get here, that will be the beat period, right, or the beat frequency, which is the difference frequency between the control clock and the sampling clock. And for these two numbers, it turns out that the beat period will be 45 nanosecond. And since the sampling clock is having a period of 5 nanosecond, I'll essentially get 9 sampling clock edges in every beat period. Okay. And thereby, I will have 9 delay values, essentially. All right. So in order to evaluate the proposed approach or the proposed solution, this is the simulation setup. Here is an example of voltage to time converter. Right, essentially, I have 3 current starved inverter and 1 normal inverter. The normal inverter will give a good rise and fall times. All right, and the analog voltage is essentially going to control the delay of these 2 current starved inverters. Okay, and this cell is implemented using GPDK 45 nanometer, and the simulation results are shown here. Although the GPDK 45 nanometer technology is pretty optimistic when it comes to the delay values, meaning the delays which is shown in simulation is slightly lower than what you could get in a commercial foundry. But the technique which is discussed here is fairly general. It is going to work when the delay is having higher dynamic range or even higher linearity. All right, so here you can see the simulation results. Here, the control clock is, the duty cycle of the control clock is set to 25%. So you can see that this purple line is the capacitor voltage. You can see that the capacitor is charging during this cycle, and then it's discharging here. And this blue dotted line is the sampling clock. Okay, so when the sampling clock edge occurs, you can see that the capacitor voltage is sampled, and the delay, right? So this red is the output of the VTC. So that this delay is a function of the voltage, which is sampled by the sampling clock. Okay, so you can see that when the voltage which is sampled is larger, you can see that the delay is going to be more. Right? That is essentially because in the VTC, the analog voltage is given to the PMOS transistor. So if this is ground, then you have the least delay. And as this value increases from 0, the delay is going to keep on increasing. Okay, so that is what is confirmed here as well. Similarly, another set of simulation results when the clock, control clock has a duty cycle of 75%. So here you can see that the capacitor voltage is high for most of the time, right? It is charging for some amount of time and discharging for the other. And you can see that when the capacitor voltage is high and when the sampling clock edge occurs there, you have greater delay. All right. So notice that the V2C, the voltage to time converter architecture is such that only the rising edge delay will depend on the voltage, right? As you can see here, the falling edge delay is fairly independent of the capacitor voltage itself, so which is obvious. All right. So if you tabulate the results for various values of duty cycles, which is shown here, from 25% to 87.5% in steps of 12.5%, you can see that during 1 beat period, we will get 9 delay values. And the 10th delay I have put here, right, to verify how periodic is these delay values, right? And you can see that for the picosecond value itself, you can see that for most of the duty cycle values, you can see that the 10th edge is actually equal, very, very nearly equal to the first delay value, except for when the duty cycle is very, very high, like 87.5%. So we don't recommend using this particular duty cycle. Okay, even then the difference in delay is about 100 picosecond, but anyway, that is not recommended to be used. All right. So then you can find out what is the average delay from these 9 delay values, and then we have that, right? And using these delays, we can interpolate from this particular graph. Okay, so given the delay, we can find out what is the test voltage which would have caused this particular delay. All right, and that is what I have tabled here. So 25% duty cycle clock would give an average delay of 578.6 picosecond, right, which would correspond to a voltage which is interpolated from that graph as around 145 millivolt. Okay, so thereby what I'm saying here is that a clock of 25% duty cycle can act as a proxy for this voltage of about 145 millivolt. Right? Similarly, a clock of duty cycle 50% can act as a proxy for about 300 millivolt. Okay, so that's essentially the crux of this paper. And then to show the results in the form of a graph, so this shows that the plot between the average delay value and the duty cycle is fairly linear. Right, and here in this particular plot, what I have done is I have captured the duty cycle and what delay it is giving. So here the 25% duty cycle is giving a delay of about 600 picosecond, and the same delay will be given by the VTC, which has input voltage of about 150 millivolt or 145 millivolt. Okay, so thereby this 25% clock duty cycle will act as a proxy for about 145 millivolt. Similarly, a clock of 50% duty cycle will act as a proxy for about 300 millivolt of voltage. Okay, so naturally, when we talk of clocks, the question will come on the jitter of the clock. What happens if you have a jitter on the clock? So if you have jitter on the control clock, that will result in a noise voltage being sampled on the capacitor, right? And if that noise is white noise with the zero mean, then the effect of that will be minimal because we are finding eventually the average voltage of the capacitor on the capacitor. Okay, so that is that. And then if you have some jitter on the sampling clock, then what happens, right? Even then it should not matter that much because essentially we are doing the average. But if the jitter is happening when the capacitor voltage is changing very fast, right, when it is charging or discharging, then if you have jitter here, maybe there could be some error in the capacitor voltage which is being sampled. Even that will be under control if you can ensure that the delay on the jitter on this clock is small compared to the time constant of this particular capacitor charging. Okay, so in order to confirm that, we have done some analysis here. So this is the voltage on the capacitor which is present. And here I'm trying to find out what is the average value of the capacitor, right? So where this delta is the duty cycle. So V times delta is the expected value or the ideal value. And then you have some other terms. So if you make the time period of the control clock much greater than the time constant of the capacitor charging, then these terms, will eventually go to zero. And typically this you can approximate it as delta minus tau by Tc into V. So this delta is the one which is the desired value. And this is the error, tau by tau C. So here in this table, I have given various values of tau by tau C. You can see here, Tc have kept a constant 5 nanoseconds. And the time constant, if the time constant is very small, then you can notice that the error is again very small, right? Whereas if the time constant is large, then the error will also grow. Okay, so probably around 225 picoseconds is probably acceptable error of about 4.5%. So this is what I have used in the simulations. All right. So in conclusion, we have proposed a simple technique for calibration of voltage to time converter based ADCs. And it has been demonstrated that a duty cycle of the clock of, let us say, 25% duty cycle acts as a proxy for about 144 millivolt, and about 50% duty cycle acts as a proxy for around 300 millivolt. Okay. And I would like to acknowledge Mr. Muralidhara, foreman of our department, for helping in the use of cadence tools, and also for the reviewers for pointing to the works of Malog especially. Okay, so thank you.
Good presentation, Dr. Rajesh, and it was really nice to understand that what work was done by you and your team. And any question from the audience? Yeah, if there are no questions from audience, I don't have any additional question also as of now. So thanks again for your presentation. And now we'll go to the next presentation of this session on test and reliability. Yeah, so that is 5B3, and that presentation topic is easily verifiable design of a non-scan sequential machines for conformance checking by Habibur Rahman, Shantanu Chattopadhyay, Indranil Sengupta, Debesh Dash, and Bhargavi Bhattacharya from Indian Institute of Technology, Kharagpur. Yeah, please go ahead, Habibur and team, with the presentation.
Hello everyone, I am Habibur Rahman. Today I am presenting the work entitled as Easy Verifiable Design of Non-Scan Sequential Machines for Conformance Checking. I acknowledge my co-authors. So the outline of the talk is as follows. I will discuss the problem and the main results. The motivation and the objectives will be mentioned, followed by the background and the preliminaries. Then I will discuss the work we have done in this paper. Then I will present the results and the discussions following the conclusion of the talk. So the problem, we discuss the problem and the main results. We have investigated the classical problem of conformance checking for non-scan sequential machines from a new perspective of design for verifiability, utilizing a machine learning framework. We use two techniques that greatly expedite the process: the insertion of augmented logic to induce the easy verifiability, and the deployment of deep neural network framework for fast prediction of output responses. In the augmented design, both test length and test time have been drastically reduced compared to that of the traditional method, such as the W method. The average test time for the augmented machines have been reduced further compared to that of the original machine when tests are conducted using the machine learning framework. Now I will discuss the motivation and the objectives. The testing of non-scan sequential machine is a challenge due to large number of states. Conformance testing is currently effective technique for testing the sequential and communicating protocols containing finite states machines. Several testing techniques have been developed for testing finite state machines. Conformance checking is a hard problem. Typically, various formal methods or simulation techniques are employed to address this issue. And however, even for moderate size FSMs, these approaches become computationally unmanageable or unable to provide adequate error coverage. So it is worthwhile to explore machine learning framework to handle this issue. For example, using deep neural networks to reduce the overall complexity of the testing. This work addresses this challenge issue and tries to develop a deep neural network based technique for FSM to reduce the overall test time. As a subset of test vectors is used, it reduces the test time significantly in resulting high-speed testing of large FSMs compared to that of the existing methodologies. So here we discuss the testing of non-scan sequential machines. It is in a non-scan sequential machine, initially the machine needs to be driven into a known state before applying any kinds of test vectors. Basically, homing sequence drives FSM to a known state, also known as the present state of the machine. Fault detection or machine verification, formerly known as the conformance testing, is solved by a test sequence known as the checking sequence. We have developed multi-layered deep neural network-based testing technique to verify whether a given FSM conforms to its specification or not. And basically, our work addresses DNN-based conformance testing techniques to detect faults within the mutant version of the FSM with reduced time complexity of the test. Given the specification of the finite state machine A, the goal of the conformance checking is to verify the correctness of the its circuit implementation B given a netlist. So now I will discuss about the DNN. So deep neural network is an artificial neural network made up of more than 3 layers, that is an input layer, the output layer, and the hidden layers. So in between these are the hidden layers where where complex computations are held in, and this is the active node of neural network. So where these are the inputs, these are the weights, and this is the output, and there is an activation function over there. So depending upon the activation function, it decides that whether one neuron will fire or not. So now this is the general model of sequential machines. So these are the primary inputs. This is the primary outputs. These are the flip-flops. And this is the combinational logic part. So now the FSM. So FSM contains of a finite number of states and generates outputs from the transition functions. So P is the input alphabet, O is the output alphabet, S is the initial state, delta is the transition function, and lambda is the output function. So this is the state diagram. Now there can be different kinds of faults which we have considered in our work. So there might be output fault, and there also might be transfer fault. So first one is the output fault, where the output has been changed. So previously it was 0, now it has been changed to 1. Now there is another fault which is the input fault, which you can see that B has previously it was A, now the A has been changed to B. So also this kind of errors might be there. So now we will discuss the proposed fault detection scheme. This work addresses the conformance checking problem in non-scan sequential circuits using 2 approaches. First one is the simulating random input sequence and observing their responses aided with a deep neural network. And the second one is given a circuit implementation of non-scan machine by modifying its netlist without using scan paths, so that it becomes easily verifiable, and in turn admits faster conformance checking. So what we did is that we first, using the backpropagation algorithm, deep neural network is trained with 80% of the input-output sequences defined by the transition functions of the FSMA. Following the transition phase, the deep neural network has been validated with the remaining output pairs that may be 20% or 30% depending upon the problem. Next, given the input sequence, it is predicted, the output is predicted, and the output is compared with that of one of the observed circuitry, which is the given implementation, and the prediction accuracy data is noted. In order to check the effectiveness of the scheme, various design errors modeled by output and the transfer fault are injected into the circuit B, and to drive the machine into a mutant version of the machine. The accuracy values observed for various mutants of machine B are recorded. High value indicate that it's a satisfactory implementation of A with zero or few errors. Experiments show improvement in the conformance with result to CPU timing and error coverage compared to the earlier methodologies in the literature. Next, we adopt a DFT strategy to modify the given non-scan circuits. In the DFT method, some extra logic is added to it to enhance the observability without using the scan path. The overhead compares favorably with that of the scan designs, and the test length and the test time are drastically reduced. As a consequence, the adoption of this strategy reduces average test time for modified machine significantly compared to that of the original machine when conformance checking is performed using the deep neural network as well. Thus, the proposed DFT offers a new mechanism to expedite the conformance checking for non-scan sequential machines. And this is the design for testability scheme. Here I will present this. So this is the this is the change in the model. So we have incorporated some extra bit over here. So this technique enhances the testability of the arbitrary non-scan sequential machine by adding an extra logic into it and extra bit. In the modified machine, any pair of states can be distinguished by observing the output of the single input vectors. The work presented by the Das et al. Theoretically proved the efficacy of the testable design, and in this work we established the effectiveness of the technique in practical sense by using the W methods. And we have you can see that when there are two methodologies. So when the C equals to 0, the circuit is acting as a normal circuit, as a normal original machine it is acting like. And when the circuit is when C is equals to 0, then it is acting as a modified machine. So this is the testable scheme which is there. So we have two cases when the flip-flops is greater than that of the primary inputs, and another case also is there. So this is the extra logic which has been added, and this is the marks. So depending upon whether it is 0 or 1. So if it is 0, then it will be acting as a normal mode, and if it is 1, it will be acting as a modified machine. So this is the second case. So here also after applying the second case, so the functionality will change. So this is the modification in the state table as we are incorporating extra logic and the extra bits over there. So the outputs will also change. So the changed outputs is like this. So the changed outputs. So Z1, Z2, Z3 has been changed to Z1 dash, Z2 dash, and Z3 dash. So this is the fault detection of the modified FSM. So steps to be performed for detecting the faults of modified FSM. So at first we run the W method to generate the test case for the original FSM. We record the test time and the test length of the original machine, and we run the W method to generate the test case for the modified machine, record the test time and the test length of the modified machine, and we compared the test time and the test length of the modified machine over that of the original machine to that of the modified machine. So this is the testing scheme. So we have the the MCNC benchmark and the ISCUS benchmark files converted into the W format method. We applied the homing sequence to initialize to the FSM, and then we have run the W method to generate the input output sequences. Then we have generated the output sequences, and we have collected the input output pairs, and we have added padding bits because they are uneven of length, and we have used the input output pairs to train and validate the neural network. We recorded the test time of the original and the modified FSM. We injected different kinds of faults, and after that we have applied homing sequence to initialize the mutant FSM, and then we have applied a subset of test vectors to train the DNN and the mutant machine. We classified the outputs of the trained deep neural network and mutant FSM, and we derived the accuracy percentage. So here is the scheme where we have implemented some padding bits over here, incorporated because they are uneven length. So in our case, we have implemented the deep neural network using the tabular method of the FastAI library, and here we have used 4-layer of architecture. So this is the accuracy percentage formula which we have developed. Now this is the experimental results. So this is the comparison of test time and test length between original machine and modified machine obtained using the W method. So this is the original W method. This is the W method on the original FSM. This is the W method on the implementation machine. So we can see that the accuracy percentage is decreasing. So the test case has been decreased up to 46%, and the test time has been decreased to approximately 57%. Now this is for the ISCUS benchmark. In the ISCUS benchmark also, the test case is average percentage is reducing up to 42%, and the test time is decreasing to 53% approximately. This is the W method over the original DNN with that of the W method with the original machine, and DNN with that of the modified machine. We have implemented DNN over the W method, and we have implemented DNN over the modified machine. So the average test time is reducing here also up to 63% approximately, and this is for the ISCUS benchmark also. So the average test time is reducing up to 37% approximately. Now this is the this is for the accuracy of mutant FSM for different kinds of injected fault. So this is for the output faults. So different amounts of faults have been injected. So we can see that with course of time, the fault rates has been decreasing. So the accuracy is decreasing from 86, it is decreasing to 51%, and hence we confirm that there are faults into our circuits, modified circuits. Now this is for ISCUS 89 benchmark also. With incorporation of faults, we can see that the accuracy is decreasing. This is for the faulty input alphabets. So this is for the transfer faults. With one fault or two faults, we can see that the accuracy percentage is decreasing with the amount of input faults into here. So this is for MCNC benchmark. This is for ISCUS benchmark also. We can see that the accuracy is decreasing. Now the conclusion. So next week we'll conclude the discussion. We have addressed the problem of design for verifiability for non-scanned sequential circuits from new perspectives of design for verifiability and machine learning framework. We adopt a technique for modifying implementation machine by adding an extra logic so that the augmented machine. The test length and the test time of the modified machine significantly reduced as compared over the original machine using the classical W method. Now the DNA-aided experiments are performed on the modified machines. All parameters such as the CPU time or the error coverage shows improvement significantly. Experimental results performed on MCNC benchmarks proves the efficacy of the proposed method. So these are the references. So thank you. Thank you for listening.
Okay. Thanks, Habibur, for the excellent presentation on your topic. And today we have two questions from the audience side. We'll go with those questions. So one of the one is the first with starting with the DNA network. So which model of the DNA network was used? That was asked by your audience, and why you have used the with the method for the test generation. That's the other associated one. Want to go ahead?
So I have used sir, I have used the tabular method of FastAI library for DNN modeling. And for the second question, why W test I have taken. So there might be different kind of test generation methodologies we can take. We can take W method, and another one is the ADS, which is the adaptive distinguished sequence. But in W method, the case is that it generates complete test sets for detecting all kinds of faults, whereas the other kinds of test patterns generation which are there, which can, like the ADS, which can detect only the transfer fault. So this is the answer of the second question. Hello, sir. Am I audible?
Yeah, you're audible. Yeah. Okay. Thank you. And one more question from the audience. What is the advantage of using the non-consequential machine over the scan-based machine?
So the thing is that in our proposed in the basic scan methodologies, so as the sorry, although the insertion of scan chains greatly simplifies testing, they can have the access to internal nodes of the machines. So they can be susceptible of different kinds of power analysis, fault injection attacks, and different kinds of side channel attacks. So the presence of scan chains may affect the ICs and implementing cryptographic algorithms, and they might be vulnerable to different kinds of security threats. And in our model, we are not injecting scan chains. We are not doing scan chains, so they are less vulnerable to all those threats. So we are so that's why we have used the non-scan methodology.
Okay, good. Any production test chip or production chip you have anything planning on this direction?
This direction, sir, I have to consult with companies and all that. So I haven't yet consulted it. So
okay,
different models I will use. Yeah. Yes.
Okay.
Thank you.
Yeah. Thank you, Habibur. Thanks for the nice presentation, and we'll go to the next presentation in this session. So we covered 3 papers, and now it is the 5B 4, that is 5B3 again. The parasitic instructions with the topic is the parasitic interactions with intermediate substrates and methods to mitigate their impact. A case study on voltage protection ICs. The authors are Srinivas Prasad, Soundararajan, and Hari Gi and Adam Withod from On Semiconductor. So yeah, please go ahead, Srinivas and team, with your presentation.
Hi, I'm Prasad. I work for Power Solutions Group on Semi Bangalore. Harry Gee is my colleague in Santa Clara, and Adam Whitworth is our ex-colleague. The paper I'm going to present is called parasitic interactions with intermediate substrates and methods to mitigate their impact. It is a case study in a supervisory product. Substrate diodes turn on and they cause parasitic BJT triggering in many products. Some cases where substrate diode itself becomes important is like charge pumps in non-volatile memories. In non-volatile memories, positive voltage generator, high voltage positive generation and high negative voltage generation also happens through a single charge pump by configuring them in bidirection. For this, it demands appropriate P and N well biasing. And if there is a forward bias of any of the substrate diodes, that can lead to failure of the charge pump or it can lead to catastrophic damage. The another case is power switches in which inductive load is driven. And when the inductive load is switched off, there should be a mechanism to take care of the recirculation currents. If it is not done, then the DMOS may be destroyed due to large VDS, or the ESD diodes will get forward biased. They will take part in the recirculation, and once they are forward biased, they will pick up an N region lying around and form a BJT that forms the collector of a BJT, and it will result in a catastrophic breakdown. Some of the well-known techniques to take care of such failures include circuit solutions like active clamping in smart switches and layout solutions using isolated guard rings or active barrier concepts. Power supervisory is yet another product line which takes care of supply ground reversals using if there are products which use multiple supplies and multiple grounds, and when there are multiple floating substrates due to these power lines, they are likely candidates for such parasitic interactions. And one case is when supply ground reversal happens. Circuits that take care of supply ground reversal result in a parasitic action. That's the case we are going to present now. A bridge rectifier is a circuit present at the input side to make sure that, say, when VDD and ground are the external supply and external ground, and there can be a misconnection in which the VDD and ground get reversed. So the supply reversal protection ensures that the internal supply, which is INT VDD, and the internal ground INT GND, are always the highest of the two. That is, the internal VDD is the highest of VDD or ground, and internal ground is the lowest of VDD or ground. So this is taken care of by this kind of a bridge rectifier configuration. When supply VDD is the higher voltage and ground is the lower voltage, this is normal mode of operation. This is not a faulty mode, and you get ion internal VDD with one diode drop initially, and internal ground again with one diode drop. But then you want to make sure that once the chip is powered up, you want to get rid of these drops. So you have a voltage detector and UVLO circuits which generate a logic signal which bypasses these diodes, so that the internal VDD is just connected to the external VDD by a switch. The diodes are bypassed. So, but during the power up, you will still face these diodes are the guys that are going to take care of the supply and ground connection. And if there is a reverse supply connection, then the logic detector indicates that there is a reverse supply, and the chip is switched off. There is no ground current flowing, so there is nothing flowing through. There is no high current at all flowing through the circuits, and a fault output is transmitted to the external flag pin. So when supply reversal happens, here is the case of a, say, in this, these are PN diodes. These are the intended PN diodes, And we should note that the P substrate of the IC is connected to the internal ground, and this switch and these switches are big switches, and all the P substrates lying around, they form from the P to this ground, they form a PN diode. To the any N diffusion lying around and this P substrate, they form a parasitic PN diode. So a leaky parasitic PN diode exists in parallel with the intended PN diode. Under the power up condition, when the rectifier is activated just before the UVLO circuit responds, there is a time window in which the internal ground is not really at 0 volt. So it will be at a diode voltage. The chip's internal ground current flows through both this junction diode and the parasitic diode while this bypassing switch is still off. Now that the PN diode is on, the internal ground to ground pad diodes turn on and the internal substrate voltage is raised. It moves up to a diode's forward voltage, and it immediately tends to pick up any collector lying nearby. In this case, here is a startup circuit that was lying next to this block, and it had a Zener's NBL layers connected to the internal supply. So they immediately formed parasitic NPNs with those NBLs in the as shown here. They are called pre-reg 1, 2, and 3, and they formed BJT structures and they drained out these supplies. And how it manifested as an issue on the silicon is the parasitic devices formed in the startup block prevented the internal supplies from coming up as expected. The silicon showed higher UVLO numbers, pushing them out of spec. If I notice here in this table, I have the UVLO rising, which was supposed to be 3.4, but on 2 units it measured very high. It is 6.5 and 6.7. Whereas on the when the supply went where once it powered up the beyond this voltage, then the switches were in action and the UVLO down was not that far off from the spec, but this was not erratically far away, but this one was too far. This was way out of spec. And when this happens, the part doesn't pass for the minimum supply voltage. The operating voltage is 5 volt, and the part failed for 5 volt of operation. When this was the signature we saw on silicon, and we we did not yet know that the startup block and the parasitic diode shown were the issue, so we did Orbits and emission test on the units to figure out the hot spots, and the startup block was shown as the hot area, and measurements of the internal ground current on ICs that had the internal on the wafer, which had the internal ground brought out, it showed about 600 millivolt. This was like a diode voltage, and then we plotted the voltage across temperature, and it showed the characteristics of the diode. So this confirmed that the part the actually the diode voltage was in action, and that was responsible for a parasitic BJT action. What we next did as a part of the failure analysis was we forced the internal ground to 0 volt and checked for recovery of the UVLO. And the moment we forced the internal ground to 0 volt, and we ramped up the supply as a very slow or a DC ramp, and then we noted the corresponding current I of input, I of n, and the blue line indicates the I of n when the internal ground was held at ground, and these were expected current numbers. They fell in line with expected current numbers, and the UVLO also recovered. But in the other case, when the internal ground was not forced to 0 volt and it was the failure case, we saw unusually unusual current numbers where they were not expected, and the UVLO was also out of spec. So this analysis indicated that if we are able to bypass the VBE diode, then the part was able to recover, and this confirmed the action of the um BJT. How to fix the issue? We decided to fix the issue, one by preventing the parasitic substrate from forming, and another is by preventing the parasitic collector from forming. So for fixing the substrate diode, if since this switch was the biggest device in that area, and if the if the P or body of the switch was free, then we could have thought about some dynamic switching of the body of the diode. But then in the configuration or in the technology we had, this had always to be connected to the internal ground of the this was not free. So we could not use this kind of dynamic switching. And even if you do dynamic switching, we need to take care that these VTs are below the VF of the diode involved. But the technology offered us Schottky diode, and we replaced these PN diodes with Schottky diodes. That was a solution we sought to take care of preventing the for one PN diode voltage over there. But the diodes are not really designed to take very high currents, so we have to make sure that the currents at startup were not that high, and it would not bump these voltages to more than 300 millivolt. And the problem gets worse at hot temperature. So here is the power up simulation we did, and what is marked here, the pink color shows the node voltage of the internal ground, which is the P side of the uh, metal side of the Schottky. That is about 240 millivolt. It does not go higher than a VF voltage or 700 millivolt. So this is quite under control. And we have also made sure that the switch MOSFETs take only 2.39 microamps, so it is not really going to carry high current to move up the voltage during power up. And we have restricted the total, we actually optimize the startup current so that it is quite low and the switches don't carry high current. When we fix the VBE or the base emitter junction this way, we try to fix the parasitic collector by preventing the collector from forming. And wherever the NBL layers were close in residence to the bridge rectifier, we connected them to ground. And or another case is we distance them as much as possible from the rectifiers. So this is what we did for taking care of the parasitic collector. Uh, Another thing is when it comes to once we make this a circuit, the EST interactions should not get into this bridge rectifier. For example, the ESD circuit exists outside between a pin and internal ground, and internal ground to the external ground. There is an ESD structure, and all the ESD has to go through, surge has to go through that structure, and it should not seek this path. So we placed a small ballast resistor here so that this PN diode does not get into action. So this guy really restricts the current. So this does not come into the ESD path. So it will not affect the IC operation normally, and it may only result in imperceptible shift in the UVLO. So thus made we presented now a parasitic triggering instance in PMIC, and how we were able to restrict the impact of it. The mechanisms of parasitic trigger was investigated, and circuit implementations to prevent the occurrence was discussed. We would like to acknowledge record our acknowledgements for our colleagues who belong to the application team and the marketing team of onsemi for their contributions and suggestions for this work. And here are some references, and this reference is particular for the guarding implementation, which is used for many power IC design for inductive recirculation. And this is from onsemi number 5. And this is a case of multiple floating substrates. You can refer these for your interest. Thank you very much.
Yeah, thank you, Srinivas and team, for the nice presentation. And it was really good to know that you have already implemented it, and it was done as an example for the voltage protection ICs as a case study. So there are no additional audience question, but I have one question on this method that you have presented today, that
Sure.
is the intermediate substrate. Yeah, hello. So the question is that other than voltage protection ICs, are you continuing these activities for other off-chip devices?
For on-chip, these are meant for on-chip devices.
On-chip and off-chip devices, anything, yeah.
Yeah.
Any other on-chip devices other than other than the voltage protection ICs? Do you think it can be considered?
Of course, yeah. You can use it for many other protection ICs, for switches or load switches and so on. Like this, we did for a supervisory IC. You can use it for any kind of voltage protection ICs, like iodine diodes and all PMICs, which have protections as their features.
And you were planning to take it forward, or it will be productized in that line?
The supervisories will be productized, yes.
Okay, thank you.
Thank you.
So with this, we'll come to the next presentation, which is the last presentation of session 5. It is the 5B4, or I think it should be the 5B5. But anyway, it is, the title is high voltage level shifter for automotive buck converter with the first transient response. And the author of this paper is Anupama Deo, Ashish Meiti, and Amit Patra from IIT Kharagpur. Please go ahead, Anupama and team.
Hello, I am Anupama Deo. I am a PhD student from IIT Kharagpur. My presentation is about a high voltage level shifter with a fast transient response which is suitable for automotive buck converter applications. I will be showing the need of a high voltage level shifter in a high voltage buck converter IC which has multiple power rails. I will walk you through the existing solutions of high voltage level shifters in literature. I will show how a conventional high voltage level shifter operates and its limitations, and I will try to address those limitations in the proposed high voltage level shifter. Finally, I will show a performance comparison, and finally, I will have the conclusion. Now let's try to understand the multiple power rails of a high voltage buck converter IC. The power stage operates from V in, the high voltage, the high side power MOSFET, which is a ND-MOS. It has a VDS breakdown of 36 volts, but it has a VGS breakdown of 5 volts, which means that the gate voltage DHS of the high side MOSFET is to be driven from V boot and VSW while maintaining a voltage swing of VDD. The controller which generates the pulse width modulated signal is a low voltage signal. So the function of the level shifter is to interface between the low voltage pulse width modulated signal and the DHS signal, which is a high voltage signal. Now let's see what are the existing high voltage level shifters in literature with comparable delays. this level shifter, it has a delay of 2.2 nanoseconds. However, it has a limitation. It uses a fast edge signal which comes from external circuit. However, this fast edge signal, it needs to be level shifted using another level shifter to bring it to this high voltage domain. Further, which means that it occupies more silicon area. Further, this high voltage domain are fixed voltage levels, which means they do not consider the challenges that come from switching in a buck converter IC. This level shifter has a very fast delay of 0.5 nanoseconds. However, the level shifting core uses two high voltage capacitors. These high voltage capacitors result in more silicon area. This level shifter has a rise time delay of 1.5 nanoseconds. However, it has a fixed tail current source in the level shifting stage, which means that it has static power consumption. Further, it will have reliability issue if the pulses that come at A and B, if they are not of sufficient level, they will not be able to trigger the recovery circuit and the level shifting action will get compromised. In another level shifter shown here, it has a delay of 2.5 nanoseconds. However, it will have static power consumption as long as the set and reset pulses are high. Further, it will have reliability issue if the inverter shown here, it is stronger compared to the level shifter, then the level shifting operation will not happen and the output will get latched. So in conclusion, the existing level shifters, they have high static power consumption and they have high silicon area. Before moving to the proposed solution, let's see how a conventional high voltage level shifter operates and what are its limitations. During the rising transient of the conventional high voltage level shifter, it has a strong pull down discharging path through these two transistors. These two transistors are basically high voltage transistors. This is the pull down transistor, and these two transistors basically they protect the low voltage cross coupled latch transistors from the high voltage pull down transistors. It has a slow charging path. As a result, it will have large asymmetric propagation delays. Besides, Vs is not pulled down all the way to VSW. It is pulled down to VSW plus VTH of this transistor. As a result, there will be a crowbar current flowing through this inverter, which means that it is having high switching power loss. Moving forward, the proposed solution addresses the problem of crossbar current in the conventional level shifter. That is done by improving the strength of the pull-up path. So I have two pull-up assist transistors. These two pull-up assist transistors, they get turned on only temporarily, and it is turned on only after the initial state of the level shifter has changed, so that the output of the level shifter is not latched. Further, I have two clamping transistors. These clamping transistors, they ensure reliability during fast transient of VSW and Vboot. So when VSW has a rising transient from ground to V in, Vs should follow that transient of VSW. Otherwise, if Vs has a voltage lower than VSW, then the voltage seen by the gate to source of this MOSFET will be higher than the breakdown limit and it will have a high voltage trace. So higher pull-up strength of the level shifter means that Vs will get pulled down to VSW easily, which means that it will have no crowbar current, which means that it will have less power dissipation, and since it is pulled down faster, it will have fast response, and since both the sides have fast response, it will have symmetric propagation delays. Let's see how the rising transient of the proposed level shifter happens. During when LS in goes from 0 to VDD, VD is pulled down to ground, Vs is pulled down to VSW plus VTHP of this transistor, Vsm is pulled up to VTHP through this weak cross-coupled PMOS transistor. Then as Vs Vs is pulled down to VSW plus VTHP, the negative edge of Vs gets turned on. During T2, since negative edge of Vs is turned on, it turns on the pull-up assist transistor M10. As a result, M10 charges VSM and VDM all the way to V boot. And since VSM is high, it pulls down Vs all the way to VSW, which is ground. So Vs is pulled down to ground and VSM and VDM are pulled up to VDD. So at this point, the level shifter output, it goes high after the T2 period. After that, a driver delay of the high side driver comes. After this period, VSW and V boot, they have a rising transient, but during this period of T driver, no transient is absorbed in the level shifter and it consumes no current. After T driver, VSW and V boot have a rising transient, which means Vs, which was at ground initially, it has to be pulled high to the new high level of VSW. So this transistor, it helps in pulling up Vs, and VSM and VDM are pulled up to V boot, to the new V boot level by the pull-up assist transistor M10. So in this period, the pull-up current during T3, it is consumed only because of this floating high voltage supply rails, V boot and VSW. Higher pull-up current in T3 will have no effect on the transient speed of the level shifter output, because the level shifter output was already high after T2 period. Now let's see what the simulation results. The circuit has been designed in TSMC 180 nanometer BCD process. The high voltage level shifter is integrated to a buck power stage with a high switching frequency of 2.1 MHz and which has an input range of 4 to 36 volts. So when Vin changes from 4 volts to 36 volts, the differential supply voltage is almost constant at 5 volts. The rise delay, it stays constant since it depends on the differential voltage. The rise delay at 36 volts is observed at 2 nanoseconds. But the fall delay, it depends on the supply voltage. So fall delay has a rising trend with the supply voltage. At around 36 volt, the fall delay is 5 nanoseconds, and around 5 volts, the fall delay is around 3 nanoseconds. The dynamic power also depends on the supply voltage. Mostly the dynamic power is dissipated because the transients in the floating supply layer occurs. So at 36 volts, a dynamic power of 1.1 milliwatts per megahertz is consumed. And around 4 volts supply, the dynamic power is 100 microwatts per megahertz. This slide shows the performance of the level shifter across process corners at Vin of 13.5 volts and a differential supply voltage of 5 volts. So for typical process corner at 27 degrees Celsius, the rise delay is 2 nanoseconds and the fall delay is around 3.7 nanoseconds, which means that less than 2 nanoseconds difference is there between rising edge delay and falling edge delay. Well, this means that This means that it has nearly symmetric propagation delays at both at the rising and at the falling edge. Now let's compare this work with the existing solutions. 2 and 4, they have better delay response. 2 has a delay of 1.5 nanoseconds and 4 has a delay of 0.5 nanoseconds, but one has static power loss and the other has large silicon area due to HB gaps, whereas this work which is presented here has a delay of 2 nanoseconds and a supply voltage of 41 volts, and it has no static power, it has no startup circuit, and it does not have any high voltage capacitors. Finally, I conclude that the presented level shifter has a fast operation. As a result, it can be used in a high switching frequency, high voltage buck converter IC. It has zero static power consumption, and it has a compact silicon area. It has reliable operation at fast transients of floating power rails. The rising delay is independent of the supply voltage and depends only on the differential floating power rails. These are the references. Finally, I would like to thank Yogesh Ramadas and Sailendra Baranwal of Texas Instruments. I would like to thank Kilby Labs, Texas Instruments USA, METI, Government of India for VLSI design tools under C2S program. Finally, I would like to thank VLSI lab members, IIT Kharagpur. Thank you.
Yeah, a very good presentation by Anupama, and we have few questions on your presentation. So first one is that, can you please clarify how does the clamping transistor improve the reliability? Can you please go ahead?
Yeah, actually clamping transistor is useful since I am using the high voltage level shifter in a buck converter IC, which is switching issue. So the one node of the level shifter, it gets pulled down to ground. But what happens is that the VSW doesn't stay at ground. The VSW rises to V in when the high side MOSFET turns on. So that node has to be raised to VSW. Otherwise, what will happen is that the low voltage P MOSFETs, which are the pull-up transistors, they will have a high voltage stress issue across their gate to source. That's why the clamping transistors actually pull up that node to VSW as VSW rises from ground to V in.
Okay.
I hope that clarifies.
Yeah, thank you. And the next question is that, what is the quotient current of the PWM? Asked by the audience.
Actually, PWM generally means pulse width modulation signal.
Yes.
Okay, so I think the question is meant that what is the quiescent current consumed by the level shifter? If that is the question, then since I do not have any static power consumption of the level shifter, then I can say that it doesn't consume any quiescent current, but while the dynamics occur, some current gets consumed when the nodes, they change their state.
Okay, good. So any current applications you have where it has been implemented, fabricated?
Yeah, actually, this high voltage level shifter is designed to be used in a high voltage buck converter. That will be helpful to give power to the electronics of the automotive vehicles, like driver assistance systems, or like the USB charger inside the cockpit of the vehicle, and rear view camera, like that.
Yeah. Okay, good. Thank you. If no other questions, then thanks Anupama and the other previous presenters. We are done with all the presentations in this session.